Hi, Meredith community. Welcome to my CSA Day presentation. My name's Whitney Watkins, and I'm a senior here at Meredith. I'm a math major, but I'm also pursuing my K6 and 6-9 teaching license in the education program. Today, we are going to go through an exploration of the four-color theorem. So go ahead and get out a piece of paper, take out all your markers and crayons, and colored pencils because we're going to be doing a little bit of map coloring to start out. And then I'm going to take you through the history of the four-color theorem, the ingredients that are needed to make this large proof, and I'm going to talk to you about who proved the original proof and a new proof that came out kind of recently. And then that'll conclude my presentation. I hope you enjoy. So first, with your coloring materials, I want you to draw this map on a piece of paper, and I want you to try to color the map using only 4 colors. So go ahead and pause the video and try to color this map only using 4 colors. But the twist is, if 2 of the regions on the map are touching, they must be colored different colors. And I think you'll find that this one's kind of simple. So go ahead and give it a try. That was easy, right? Awesome. Let's move on to a little bit of a harder one. So now color this one with no more than 4 colors. So try to draw it and color it with 4 colors. Pause the video. I'll wait. Alrighty. That one was a little bit harder, right? I would agree. Now for the ultimate challenge. Color this one. I'm just kidding. You can save that for a later date. Let's move on with the presentation. So what is the four-color theorem? Well, it's stated very blandly, but straightforward. Every map can be colored with at most 4 colors in such a way that neighboring countries or regions are colored differently. That is the four-color theorem. So let's dig deeper into that. So based off of what I just stated, let's clarify what's a valid coloring and what is not a valid coloring. If you look at the first map that has the check underneath it, this is a valid coloring according to the four-color theorem because you can see there are 4 regions and all of the regions are touching each other because their boundary lines are adjacent to all the other regions. Therefore, none of them can be colored the same color. That's why there are 4 colors used and every region is a different color. If you look at the second example with an X underneath, you can tell that this is not a valid coloring because that center region is blue, but the region above it is also colored blue, and those 2 regions are neighboring regions, and they're not supposed to be colored the same color. So that would be in violation of the four-color theorem. So, how did this all start? Well, I'm going to give a little bit of a story time from my paper, my thesis. So, the four-color problem was initially stated as a curiosity formed by a college professor in England. In 1852, a mathematics professor at the University College in London, Augustus de Morgan, wrote a letter to his friend Sir William Hamilton, an Irish mathematician. And in the letter, De Morgan explains a question that was posed to him by one of his students. According to the letter, the student asked, and I quote, "If a figure be anyhow divided and the compartments differently colored so that figures with any portion of common boundary line are differently colored, 4 colors may be wanted, but not more. Query, cannot a necessity of 5 or more be invented?" That's some fancy English language. And through this question, the four-color theorem was formed. So, the student to whom De Morgan was referring was Frederick Guthrie, who later became a physics professor. Frederick Guthrie did not just wake up one morning wondering whether or not you needed four colors to color a map, but his inquisitiveness surrounding the topic was inspired by his brother, actually, Francis Guthrie, which you can see in this picture. And Francis was coloring a map of the counties of England, and while he was coloring, he proposed the question to his brother, and his brother proposed the question to De Morgan, where he proposed it in the convention that I mentioned previously. So that's kind of some background as to how this four-color problem was born. So let's go ahead and try to define a map, because you can't really go into map coloring just assuming things about maps. There has to be strict guidelines that we have to follow so that everyone's on the same page. We're talking about map coloring and what we're coloring in terms of maps. So to define a map, firstly, every map consists of a specific amount of regions. So if you look at this visual, you can see that that map has 3 regions. Secondly, every region contains boundary lines that serve as borders to the region. Thirdly, all the boundary lines intersect with other boundary lines at meeting points. So if you look at the visual, those purple arrows are pointing out the 4 meeting points of that map. Fourth, 2 regions that have a boundary line in common are called neighboring regions. So basically, regions that are next to each other are called neighboring regions. So to continue, any 2 neighboring regions must be colored differently according to the four-color theorem. So as you see in this picture, all the regions in that map are colored differently because they're all neighboring. When 2 regions meet at a single meeting point, one is allowed to color them the same color. And lastly, it is required that every region of a map must be in one piece. So if you look at the picture, you can see that region A is not in one piece, therefore that whole map is not valid, according to the four-color theorem. Maps as networks. So a lot of people throughout history, like century-long history, were working on this problem. And as work progressed on the four-color theorem, map coloring became more and more intricate. Just like when you try to color that map of the United States, it can get very intricate very fast. So to kind of make it a little bit more simple, maps were drawn as networks. So a dot was representing a whole region, and a line connecting 2 dots showed that 2 regions were neighboring. So you can look at those visuals and see the original map of the US being colored, but also underneath you can see it drawn as a network. And that's what the mathematicians worked with when they were solving and trying to prove the four-color theorem. So what was the goal of the proof? There we go. So the goal or the target, as you can see in the visual, of the proof was to find the unavoidable set of reducible configurations. It's a mouthful, isn't it? So the avoidable set of reducible configurations is a list of those networks that I mentioned before where any and all maps could be reduced to one of the networks in the list. Every network in the list is four-colorable, of course, and every network contains at least one configuration from the unavoidable set. And every network means any map that anyone could draw contains at least one configuration from the unavoidable set. So let's talk about the 2 main ingredients that mathematicians used to try to solve the four-color theorem. These 2 main ingredients were discharging and reducibility. So let's talk about discharging first to try to find unavoidability. So the discharging method was created by a mathematician named Heesch. He was German. And discharging is defined as a strategy where regions of a map are assigned charges depending on the number of sides of the regions and how many sides the regions possess. And the charge is distributed throughout the map. So to be more specific, each region has a charge, as I said, and each region with K boundary lines or K edges has a charge of 6 minus K. So if you look at the visual at the top, you can see in the middle of the first map, there's a pentagon, and it says the charge of that pentagon is 1 because the pentagon has 6 sides, so the K would be 5. A pentagon has 5 sides, so the K would be 5, and you would do 6 minus 5, which makes the charge of the pentagon 1. And then through the discharging method, you can see that that charge is distributed amongst the other regions surrounding the pentagon in the center, and that's the resulting picture in the second half of that visual. And the reason why the discharging method is so important is because this method created an unavoidable set, which is a collection of configurations where at least one of which has to appear in every map in order to be four-colorable. And the unavoidable set is seen in the second photo. So every map has to include at least one diagon or triangle or square or 2 adjacent pentagons or a pentagon adjacent to a hexagon. And in the unavoidable set of reducible configurations, every network has at least one of the configurations from the unavoidable set, which was determined through the discharging method. Moving on. The second ingredient is reducibility. Reducibility was researched and created by George D. Birkhoff in his writing called The Reducibility of Maps. And he determined 6 ways to find whether or not a map is reducible. A map is reducible if it does not contain a minimal counterexample, which means a map with the least number of regions that cannot be colored with 4 colors. These were proven to not exist, which is why they are called minimal counterexamples. Because if they did exist, then we wouldn't be able to call the Four-Color Theorem a theorem because it wouldn't have been able to be proven. But I'm going to briefly introduce the 6 reductions that Birkhoff wrote about in his paper. So the first reduction states that if more than 3 boundary lines of a map meet at a vertex, the coloring of the map may be reduced to a coloring of fewer regions. You can see that in the first visual with the 4 regions, 1, 2, 3, and 4. And since they all meet at one vertex, we can eliminate regions 2 and 3 and color them the same color. The second reduction says if any region of a map is multiply connected, meaning the region has a hole in it, the coloring of the map may be reduced to a coloring of maps of fewer regions. You can see that in the second visual through those 4 steps. The third reduction states that if 2 or more regions form a multiply connected region, the coloring of the map may be reduced to the coloring of maps of fewer regions. It's very similar to the second reduction. The fourth reduction says if the map contains 1, 2, 3, or 4-sided regions, the coloring of these maps can be reduced to the coloring of a map of fewer regions. And you can see that in the fourth visual. And then the fifth and sixth reduction address something called Kemp chains and rings. And Kemp chains are essentially alternating the colors of a chain of regions that form a ring or in a circle. And you just alternate the colors so you don't waste too many colors because you're trying to color the map with 4 colors or less. So if you have a ring of regions, you can just alternate the colors to save the other two colors for other regions. So what was the result? Well, we fast forward in time a little bit. We come to Kenneth Appel and Wolfgang Haken, and they proved the Four-Color Theorem in 1976. They were able to create the unavoidable set of reducible configurations, and their proof contained 1,476 cases, which means the unavoidable set they created had 1,476 configurations. It was a lot of work for them. But they used the discharging method from Heesch and the rules of reducibility from Birkhoff to come up with this unavoidable set, which is a large list of networks. Of course, with success, there are criticisms. So, Kenneth Appel and Wolfgang Haken received lots of criticism for their proof because, one, the computer was used to find unavoidability, and so when they used the discharging method, which contained a lot of rules, they used a computer to do so, and the people who were trying to verify that the proof was valid could not hand check this portion of their proof. Also, there were too many cases, so the checking for reducibility by hand was still incomplete to this day because the process of checking the proof was long and tedious. So the legitimacy of the proof decreased because of the use of computer, because in the 1970s, it was unheard of for mathematical proofs to be proven using the computer. So people were having trouble trusting it over man and over the human brain because they thought that using a computer to prove a math proof it could lead to error, basically. With this said, a few decades later, a new proof was written. In 1994 by Neil Robertson, Daniel P. Sanders, Paul Seymour, and Robin Thompson, and they decided to write their own proof of the Four-Color Theorem just because they were of the few people who were trying to verify the old proof in 1976, and as they were hand checking the configurations to make sure they were unavoidable and reducible, they found the process tedious as well, so they figured, okay, let's figure out a way to make this proof shorter and easier to check and just make our own proof. And so as a result, their proof contained, instead of 1,400 cases, their proof contained 633 cases. And this was due to a new discharging procedure where they were able to have 32 discharging rules because of a conjecture that was proven by Heesch that I would like to share. Here it is. Here's the conjecture that they were able to prove. It stated that a reducible configuration can be found in the second neighborhood of an overcharged vertex, which is a vertex with a charge that has changed from negative to positive. The second neighborhood is the set of all regions that are not themselves adjacent to a given region, or also known as the overcharged vertex. So by proving the second neighborhood of any region with excess charge always has a reducible configuration, Robertson, Saunders, Seymour, and Thomas were able to avoid some of the obstacles that Appel and Haken encountered. And these are the features that make their proof of the Four-Color Theorem much, much, much shorter. You can look in this visual to see what I was talking about with the networks. This is a part of the unavoidable set of reducible configurations that was included in the new proof. So to compare the two proofs, as far as logistics, Appel and Hawken had, as I said, 1,476 configurations in their unavoidable set of reducible configurations. And believe it or not, with that discharging method, they had 481 discharging rules, which is why they needed to use a computer. But with the new proof in 1994 by Robertson, Saunders, Seymour, and Thomas, they had 633 configurations in the unavoidable set of reducible configurations, and they were able to knock it down to 32 discharging rules. So this concludes my presentation. If you have any questions about some of the proofs and a lot more of the math behind this story, please let me know. I kind of just scraped the surface with this presentation, but I hope you learned a lot, so please leave a comment under my video, or if you have a question, also leave a comment there. Here's my references. Thank you so much for taking time out of your CSA day to watch my presentation. I really appreciate it, and I hope all of you stay safe and healthy during this time. Bye!